So we went through lung compliance and now we're going to look at airway resistance. So again, we talked about the dynamic and static compliance and we looked at kind of some mathematical applications of that. Now we're going to look at airway resistance, and airway resistance is underneath that title of frictional forces. All right, so thinking about air moving through the bronchioles, the bronchi, and the resistance that creates. That's what we're going to be looking at here. So frictional forces only matter during dynamic conditions when the air is actually moving, which we talked about previously for the dynamic compliance. So when air is moving, we are concerned about these frictional forces. The two frictional forces that we talked about were the tissue resistance or frictional resistance with tissues moving. I gave the example of how with the parietal pleura and the visceral pleura, there's fluid in between them to help to kind of lubricate that movement of the lungs inflating and deflating so that you're hopefully eliminating some of that frictional resistance. But the kind of the big cajone of these frictional forces is going to be your airway resistance, and that's going to comprise 80% of your frictional forces. So if you're looking at airways and the resistance of the flow going through them, what you're going to be talking about is Poiseuille's law. I'm never going to make you mathematically apply Poiseuille's law. There are people who are math-minded, and so I include slides that show these equations because for some people that is much more clear than a definition. I am not one of those people, but for some people, that's the way it works. So I don't like to take them out, but just know from a technical standpoint, I'm never going to be getting that detailed with it. It's just kind of important to know that that's the physics law that we're talking about here. So based on this law, work of breathing is going to increase by 16-fold when the radius of an airway is reduced by half. And kind of the big takeaway for this is a very small reduction in the radius, which would be the size of an airway, will increase how hard someone is going to have to work to breathe. Okay? And we care about this because there's a lot of things that can affect the radius of your airway. If you have a bronchospasm, so your bronchioles, your bronchi, all of your airways have smooth muscle, and that smooth muscle can spasm irregularly and really kind of clamp down that airway. Asthmatics, COPDers, allergic reactions, anaphylaxis can cause this. The other thing that can cause a reduction in that airway diameter, radius, is if you have mucus that's not being cleared out properly. That can create blockades as well. If you have fluid that doesn't belong there. So there's a lot of things that can affect that and really increase your work of breathing. And when you're talking about airway resistance, you can kind of just link in your mind that we're talking about Poiseuille's law. This is a kind of a synopsis of what I just said. In a nutshell, what you need to know: the airways, bronchi, bronchioles get smaller, gas flow slows down or stops. So you can think about it as impeded. These are some of the things that we just talked about that can make airways smaller. Oh, excuse me. Okay, so airway resistance equals the impedance of gas flow through the airways. Okay, the blockage of gas flow through the airways. The mathematical application of this is going to use some familiar terminology and numbers, and then something new. So you're going to use your peak inspiratory pressure from previous. You are going to minus your plateau pressure. So if you can kind of remember that pressure time curve, there was the difference between that pip and plat, and that's what you're going to be solving for here. So you'll get a number for your peak and a number for your plat, and the difference between them is going to be your top number. And so your pressure is measured in centimeters of water pressure. That's the unit that we're using there. On the bottom of this equation, you're going to be looking at flow. And flow is going to be in liters per second. Okay, so you're going to have your pressure on top and your flow on the bottom. It's the total units for this equation are centimeters of water pressure per liter per second. It's kind of a mouthful, but this is coming from the top, that pressure, and then flow is liters per second. You can kind of think about it the same as miles per hour in a car. It's a measure of movement, okay? So flow is in a liter per second. Yeah, so this is where those numbers are coming from. The normal range for airway resistance is 0.5 to 2.5 centimeters per liter per second, okay? This is just kind of showing a normal airway, nice and open, that gas flow shouldn't be impeded. This is kind of an example of the smooth muscle and how it circles the airways. This is an airway that's bronchospasming. You can see that smooth muscle is contracting down. It's inflamed. You have swelling of that tissue. You have mucus in there. So this is obviously going to be an airway that's impeding the flow of the air. That's going to have a high airway resistance, low airway resistance. One of the things that you can see with patients is in the larger airways, you have this very turbulent airflow, okay? And most of your airway resistance actually occurs in your larger airways. So they say that it accounts for 80% of your total airway resistance. And what's interesting is it's on purpose that the air is so much more turbulent in the conducting zone. We learned about the conducting zone and the respiratory zone. So your larger airways are in the conducting zone. And one of the advantages of this very turbulent airflow, where you have this high airway resistance, is it forces kind of the air to slam into the sides of your bronchi. And when it does that, all the different pollutants that can come in from the air, or the irritants, the hair, the pollen, all the different things that you inhale with every breath that you take, because you have this turbulent airflow that's making it kind of impact to the side of your airways, then that's where those cilia and your secretions can stick irritants so that they don't make it down into the respiratory zone, so they don't make it down where you have gas exchange happening. So your large airways, very turbulent airflow, higher airway resistance, 80%, and it helps to kind of remove those irritants and pollutants. When you move into that respiratory zone, we have those very, very small, thin bronchioles, and that's where your gas exchange is happening. You get what is called a laminar gas flow or airflow, and all that means is that air slows way down. It's much less turbulent. It's more organized. You can almost think of it, I guess, more neat. And that makes sense when you think about the fact that you're now in a more delicate area of the lungs. You have thinner tissue because you want that very, very thin-walled alveoli. You want it to just be one cell thick because you're really trying to get the most efficient gas exchange that you can. So this is only going to account for about 20% of your airway resistance. It's much more smooth and low pressure airflow when you get into that respiratory zone. This kind of shows you that graphically. So you have airway resistance, centimeters of water pressure per liter per second. And you can see this kind of shows the trachea to the bronchus to the bronchioles. So you can see you have like these large airways and they move down and they get smaller and smaller and smaller as you make your way to the respiratory bronchioles, to the gas exchange area of the lung. And you can see lots and lots and lots of airway resistance, and then it drops off as you're moving down to those smaller airways and that more laminar gas flow. So when you're applying this from a mathematical standpoint, what we're going to be looking at, and this is just kind of a, I don't know if this is helpful to everybody, this graph, but this kind of shows a similar one to the ones that we were looking at before, where you have your peak inspiratory pressure, that change in pressure right here, your plateau pressure, and then you're coming down to the PEEP. So when you're looking at your peak minus your plat, this is just showing you that change in pressure, that difference in pressure, divided by flow. So if you come to the top here, we'll call that number 20. The PIP is 20, and then you follow it down, and the plateau pressure is 15. So if you were going to be solving this, you would take that 20 minus the 15, and your difference in pressure would be 5. And then you would just divide it by the flow in liters per second. The second thing I'm going to talk to you guys about, and this dot should be over here. My formatting sometimes sucks with those dots. They drift around. But a lot of the times that you get flow, you actually get it in liters per minute, not liters per second. So there's kind of an extra step in this equation. So you can figure out the difference between your pip and your plat, but then you have to convert your 40 liters per minute to 2 liters per second. So I'm going to show you how to do that here. And that's going to be how we're going to calculate our airway resistance. Airway resistance is abbreviated RAW, so R with a small AW. So if you think about, and I should look at what the next slide is. Yes, okay. So if you think about this equation that we just talked about, you have your RAW or airway resistance as your change in pressure over flow. We talked about how the change in pressure specifically that we're talking about is peak minus plateau pressure. And then you're going to divide it by the flow. So you have the 20 minus the 15 to give you the 5. Now we need to convert this 40 liters per minute to liters per second. To do that, you simply take the 40 and you divide it by 60 seconds, okay? That's going to turn it from liters per minute into liters per second. So your new equation over here is 5 centimeters of water pressure divided by 0.67 liters per second, and you should end up with 7.46. You could round that to 7.5 centimeters per liter per second. We said that the normal is 0.5 to 2.5. So obviously this is much bigger than the normal range, right? So the high end is 2.5, this is 7.5. So much higher than the normal range. So what this is showing is high airway resistance. We don't want high airway resistance, right? We don't want an impedance to gas flow. We want gas to move freely and easily through the lungs, right? We don't want to increase that. So this would be high airway resistance. Okay, so for the lecture questions on this one, what law is going to correspond to the airway resistance? Name the 3 things that can increase it. Go through these and really kind of think about the way that airway resistance would contribute to making it more difficult for a lung to inflate and why that would be a problem for your breathing. Again, the 2 big things that we talked about for this unit are lung compliance, or the stretch of the lung, and you have a normal value for that. And then this is airway resistance. This is the other big force that really opposes lung inflation and the different things that can affect that.